Hello science fans, Bill Nye here. Are you ready for an absolutely fantastic, incredibly groovy, and super scientific adventure today? We are going to build something amazing right in your own home. Yes, you heard me correctly. We are diving into the world of do-it-yourself projects, and our mission, should you choose to accept it, involves creating your very own lava lamp. This isn't just about making something that looks cool. Oh no, it's much more than that. It's about exploring the wonders of science in a fun, hands-on way. So get your science hats on, because we're about to embark on a journey into the land of density, polarity, and chemical reactions. By the end of this, not only will you have your very own groovy lava lamp to show off, but you'll also understand the scientific principles that make it all happen. Let's get ready to mix, bubble, and learn. Alright, future scientists, before we can start our amazing lava lamp construction, we need to gather our materials. First on our list is a clear container. This could be a clean plastic bottle, perhaps a 1-liter fizzy drink bottle, or even a tall glass jar. Next up, we need some good old H2O, also known as water. Just regular tap water will do the trick perfectly. About 1/4 to 1/3 full for your chosen container should be about right. Now, for the lava part of our lava lamp, we need some oil. Vegetable oil is a fantastic choice for this experiment. Finally, to bring the color and the bubbles, we need 2 more essential items. First, food coloring. Pick your favorite vibrant shade, red, blue, green, yellow, or even mix them to create your own unique hue. And for the bubbling action, the star of the show, Alka-Seltzer tablets. These fizzy tablets are what will make our lava lamp come alive, creating the gases that lift the colored water up through the oil. Gather these gizmos, and let's get ready to build. Science is thirsty work after all. Let's get started. Alright team, are all your scientific supplies gathered and ready? Excellent! Now comes the really exciting part, assembling your very own DIY lava lamp. First, take your clean, clear bottle or jar. Carefully pour the water into your bottle until it's about 1/4 to 1/3 full. Once your water is in the bottle, it's time to add a splash of color. This is where your food coloring comes into play. Gently add about 5 to 10 drops of food coloring into the water. You can give the bottle a tiny, gentle swirl to help mix the color in evenly. Now for the next layer in our liquid sandwich, it's time to add the oil. Slowly, and I mean slowly, pour the vegetable oil into the bottle on top of the colored water. You'll want to fill the bottle most of the rest of the way with oil, leaving about 1 inch or 2 of space at the very top. Observe what happens as the oil meets the water. You should now see 2 separate layers in your bottle, the colorful water sitting calmly at the bottom, and the yellowish or clear oil floating majestically on top. This separation is absolutely crucial for our lava lamp to work. Take a moment to admire your layered liquids. You've just created a simple density tower, but the real show is yet to begin. We've set the stage, and now it's almost time to introduce the catalyst that will bring our lava lamp to life with bubbling, flowing motion. The moment of truth has arrived, science explorers. Your bottle is prepped with its beautiful layers of colored water and oil. Take 1 Alka-Seltzer tablet from its packaging. You might find it's quite a large tablet, so it's often a good idea to break it into a few smaller pieces, perhaps 2 or 4. Now, very carefully, drop 1 or 2 of the Alka-Seltzer pieces into your bottle. Try not to splash too much. As the tablet pieces sink down through the oil layer, they won't do much. But just wait until those pieces hit the colored water layer at the bottom. That's where the real magic, or rather, the real chemistry begins. Observe closely as the tablet interacts with the water. You should start to see tiny bubbles forming around the Alka-Seltzer pieces as they rest in the colored water. These bubbles are a gas, and they are the driving force behind our lava lamp's motion. Keep adding small pieces of Alka-Seltzer as needed to keep the show going. Density unveiled. So you've seen your homemade lava lamp in action, with those groovy blobs of color rising and falling. It's pretty spectacular, isn't it? But what's the science behind this magical motion? One of the main scientific principles at play here is something called density. Density is basically a measure of how much stuff is packed into a certain amount of space. In our lava lamp we have 2 main liquids, water and oil. As you observed when you poured them into the bottle, the oil floated on top of the water. This happens because water is denser than vegetable oil. So the heavier, denser water sinks to the bottom and the lighter, less dense oil floats on top. In our lava lamp, the colored water is initially at the bottom because it's denser than the oil. It stays there quite happily until something else comes along to change the situation. That something else is, of course, our fizzy friend, the Alka-Seltzer tablet. When the Alka-Seltzer creates gas bubbles, these bubbles attach to the water. Now, a blob of water filled with gas bubbles is suddenly much less dense than the oil surrounding it. This makes the blob float upwards through the oil. Once the gas escapes at the top, the water blob becomes dense again and sinks back down. This up and down movement, all driven by changes in density, is the heart of our lava lamp's groovy dance. Section 6. More science, why oil and water don't mix, polarity pals and foes. Now let's tackle another fascinating question. Why don't oil and water mix together to form a single liquid? You saw it clearly when you poured them into the bottle. They formed separate layers. The reason they don't mix is down to something called polarity, which is all about the way molecules behave. Think of molecules as tiny little magnets. Some molecules have a positive end and a negative end, a bit like the north and south poles of a magnet. These are called polar molecules. Water, H2O, is a fantastic example of a polar molecule. It loves to stick to other polar molecules. Oil molecules, on the other hand, are different. They are nonpolar. This means they don't have those distinct positive and negative ends like water molecules do. They are more electrically neutral all over. So, what happens when you try to mix polar water with nonpolar oil? Well, it's a bit like trying to get magnets to stick to pieces of wood. The water molecules are much more attracted to each other than they are to the oil molecules. They huddle together, pushing the oil molecules out of the way. Similarly, the oil molecules are more comfortable sticking with other oil molecules. This is why they form separate layers. Without this property, the food coloring would just disperse throughout the entire mixture, and you wouldn't get those distinct colorful blobs moving up and down. Section 7. The Bubble Bonanza, Alka-Seltzer's chemical reaction. We've talked about density making things float or sink and polarity keeping our oil and water separate. But what about those amazing bubbles? What exactly happens when an Alka-Seltzer tablet hits the water to create that fantastic fizz? This, my friends, is where we dive into the exciting world of chemical reactions. An Alka-Seltzer tablet isn't just one single substance. It's a clever mixture of a few different chemicals, primarily sodium bicarbonate, you might know this as baking soda, and citric acid, the same stuff that makes lemons sour. When these chemicals are dry, they just sit there, minding their own business. But add water, and everything changes. When the Alka-Seltzer tablet dissolves in the water, the sodium bicarbonate and the citric acid are finally free to meet and react with each other. This meeting isn't just a friendly handshake, it's a chemical transformation. The sodium bicarbonate and citric acid undergo a reaction that produces a brand new substance, carbon dioxide gas, CO2. This is the very same gas that makes fizzy drinks bubbly, and it's the gas we breathe out. You can't see the individual gas molecules, of course, but you can definitely see the bubbles they form as they group together in the water. This continuous process of gas production, lifting, gas release, and sinking is what creates the mesmerizing cyclical motion in your DIY lava lamp. Section 8. Seeing the unseen, thermal cameras, and glowing fun. Now that your lava lamp is bubbling away, let's explore more ways to observe this phenomenon. If you have a thermal camera, you can see your lava lamp in a whole new way. Thermal cameras see heat or infrared radiation. Everything gives off heat, creating images based on temperature differences. Imagine what your lava lamp looks like through a thermal camera. What might you see? The Alka-Seltzer reaction can be slightly exothermic or endothermic. A sensitive thermal camera might pick up subtle temperature changes. Warmer blobs might appear as warmer spots moving through cooler oil. It's an experiment within an experiment, exploring thermal properties. This is what science is all about, asking what if, and finding new ways to observe. But what if you don't have a thermal camera? Don't worry, there are still plenty of ways to make your lava lamp experience even more spectacular. Section 9, the grand finale, science is super cool. And there you have it, science adventurers. You've built your very own DIY lava lamp and explored the science behind it. From density to polarity, and the Alka-Seltzer reaction, you've seen it all come together. Science is all around us in the most unexpected ways. Keep asking questions and keep having fun with science, because science is super cool. Bill Nye signing off.